You sign up on an app, one action. But behind the scenes, your system now needs to do 6 things simultaneously. Send a welcome email, fire an analytics event, push a mobile notification, log to Slack, update the in-app badge, trigger a fraud check. And your API is doing all of this directly, synchronously. एक सर्विस स्लो हो गई, say SendGrid is having a rough morning, your entire API call is now blocked. Request timeout, user gets a 500 error. Not because your code is broken, but because some external service you depend on hiccups for 2 seconds. And it gets worse. Now say you have 10,000 users signing up per minute during a sale. Your API is hammering SendGrid, Twilio, and FCM directly. You've become every provider's nightmare customer. This is tight coupling. And this is why notification systems at scale break in very specific, very painful ways. तो आज हम इस प्रॉब्लम को properly solve करेंगे. Full system design, every layer, every trade-off. Let's start with what we are actually building. Before we draw a single architecture box, we define requirements. Skip this step and you'll build the wrong system with confidence. Functional requirements first. We need to support 4 notification channels: push notifications, email, SMS, and in-app. Users should be able to control what they receive. Opt out of marketing emails. Set quiet hours. Say, don't disturb me between 10 PM and 8 AM. We need a template engine. Marketing team को हर notification के लिए deploy नहीं करना चाहिए. They should own the copy. 2 types of notifications: transactional, like OTPs and order confirmations, and marketing, like offers and re-engagement. These have very different SLAs. And we need delivery status: sent, delivered, opened, failed. We want to know. Now, non-functional. Scale: 50 million users, 500 million notifications per day. That's roughly 5,800 notifications per second at peak. Latency: OTPs and transactional push, P99 under 3 seconds. Email: P99 under 30 seconds. Marketing notifications: best effort, minutes is fine. Availability: 99.9%. That's 45 minutes of downtime per month max. And this one is important. At least once delivery with idempotency. हम notification miss नहीं कर सकते, but we also can't send the same email twice. These 2 requirements together define most of our architecture decisions. Keep them in mind. Let's build the architecture. I'll introduce each component one at a time, and we'll see how they connect. Layer 1, the trigger. Everything starts from a client action. User sign up, order placed, payment received. This hits our API gateway. Auth layer validates the request. Then it goes to the notification service. The notification service does one thing. It takes the incoming event, validates it, enriches it with metadata, and publishes it to the event bus. It does not call any provider directly. Bilkul nahi. Layer 2, the event bus. This is the heart of the system. The notification service publishes one event. The event bus fans it out to multiple workers, independently, in parallel. Each worker owns one channel. The push worker doesn't know about email. The email worker doesn't know about push. They are completely decoupled. Layer 3, the filter and render. Before any worker sends anything, it checks the user preference service. Does this user even want this notification on this channel? Quiet hours check, frequency cap check. Then template service renders the content, takes the template ID, injects variables, returns the final message text. Layer 4, the providers. FCM for push, SendGrid for email, Twilio for SMS. Workers call providers through adapters, a thin wrapper that handles provider-specific auth, retry headers, and response parsing. If we ever swap SendGrid for Mailgun, only the adapter changes, nothing else. Layer 5, data. PostgreSQL for persistent data, user preferences, templates, notification logs. Redis for speed, deduplication cache, rate limit counters, preference cache. This is the skeleton. एक बार पूरा path देखो, user action से लेकर delivered notification तक. 6 service boundaries, 0 tight coupling. Now let's go deep on each piece. The event bus is where the most important decision of this design lives. Kafka or SNS? Both fan out events to multiple consumers, but they are very different tools. Use Kafka when you need strict ordering. If an OTP must arrive before the welcome email for the same user, Kafka guarantees this via partition ordering. You need event replay. Provider was down for 2 hours. Kafka retains messages for 7 days. Replay everything. SNS? Gone. No replay. You're building an audit log. Every notification event stored, queryable. You control your infra and want fine-grained control over consumer groups. Kafka में partition की होता है user ID. Same user के सारे events same partition में जाते हैं. This guarantees ordering per user. Partition count equals parallelism. 100 partitions, 100 parallel consumers. Each channel type has its own consumer group. Consumer group keeps its own offset pointer. Email worker pausing doesn't affect push worker. Complete independence. Use SNS+SQS when you're on AWS and want a fully managed setup. No Kafka cluster to operate. You want automatic fan-out without managing consumer groups. You need per subscriber dead letter queues out of the box. SNS के साथ setup simple है. One topic, 4 SQS subscriptions, 1 per channel. SNS delivers to all 4 simultaneously. Each SQS queue independently scalable. SNS also has message filtering. Marketing notification, route only to email and push. Skip SMS. You define filter policies per subscription. No code required. For our system, अगर AWS पे हो, SNS+SQS is the pragmatic choice. If ordering and replay matter or your multi-cloud, Kafka. We'll use SNS+SQS for this design. Managed, battle-tested, scales automatic. Let me tell you the most annoying thing you can do to a user. Spam them at 2 a.m. with discount offers they never asked for. This chapter is about respecting your users and also not getting your app uninstalled. The preference service sits between the event bus workers and the providers. Every message passes through it. No exceptions. For each user, for each channel, for each notification type, we store is it enabled? What are their quiet hours? What time zone are they in? User ने marketing emails के लिए opt out किया, we never call SendGrid for them. Simple as that. The filter runs 4 checks in sequence. First, is the channel enabled for this user? If no, drop it immediately. Second, is this notification type allowed? Transactional notifications, OTPs, order updates, these bypass most preferences. Marketing notifications respect all preferences. Third, quiet hours. Take the user's time zone, convert current time, check if it falls in their quiet window. यहाँ एक subtle bug है. Don't store quiet hours in UTC. Store the user's local time and their time zone strings separately. UTC offsets change with DST. Time zone strings like Asia, Kolkata handle this automatically. Fourth, frequency cap. In Redis, frec::user ID::push::1h, increment this key. Set TTL of 1 hour on first write. If the count exceeds 3, drop the notification. Or better, route it to a scheduled retry queue to try again after the window resets. Marketing notifications that hit quiet hours don't get dropped, they get delayed. Scheduled for first available window. User wakes up, gets the notification at 8 a.m. Better experience, better delivery rate.
Why does the template engine deserve its own layer? Because notification copy changes constantly. A/B tests, new languages, seasonal campaigns. If every change requires a code deploy, your marketing team will hate you. Templates are stored in a database. Each template has a channel, a locale, a subject line for email, and a body with handlebar style variables. Hi::name, your order::order ID has shipped. Expected delivery: :delivery date dot full stop. At render time, the worker fetches the template by ID, channel, and locale. Injects the variables from the event payload, out comes the final message. Locale support, same template ID, different locale row. यूजर के सिस्टम लैंग्वेज के अकॉर्डिंग ऑटोमेटिकली सही लैंग्वेज में नोटिफिकेशन आएगा. टेम्पलेट्स कंपाइल टू अ रेंडर फंक्शन एंड गेट कैश्ड इन रेडिस विद अ 1 hour TTL. Thousands of notifications per second, सबके लिए सेम टेम्पलेट. रेडिस से मिलेगा, डेटाबेस पे लोड नहीं. One more thing, sanitize the output. Template variables come from user data. Injection attacks are possible. Strip HTML from SMS body. Escape special characters in push title. A template engine is also an attack surface.
This is the reliability chapter. यहाँ गलती की तो double notifications जाएंगे. पैसे वाली गलतियाँ. Let's talk about what happens when a provider call fails. SendGrid returns a 503. Transient error. Maybe they're deploying. We should retry. But how? SQS handles this natively through visibility timeout. When a worker picks up a message, SQS hides it from other workers for a configurable window, say 30 seconds. This is the visibility timeout. If the worker fails to delete the message before this window expires, SQS makes it visible again. Another worker picks it up. Automatic retry. But we don't want to hammer a failing provider every 30 seconds. Exponential backoff. First retry after 1 second. Then 2, then 4, then 8, then 16. After 5 retries, we give up and move the message to the dead letter queue.
Dead letter queue पे message आना means something is structurally wrong. Either the payload is malformed or the provider is having a long outage. Either way, a human needs to look at it. DLQ depth greater than 100, pager duty alert fires. On-call engineer inspects the messages, fixes the bug, or waits for the provider to recover, then drains the DLQ back to the main queue. Now, idempotency. SQS is at least once delivery. Network hiccup के बाद same message twice deliver हो सकता है. Without protection, user gets 2 welcome emails or 2 OTPs. That's bad. Before processing any message, the worker constructs an idempotency key, user ID, event ID, and channel concatenated. Then it does a Redis set with NX flag and 24-hour TTL. NX means set only if not exists. If the key is already in Redis, message was already processed. Skip it. If key is not there, process it, then set the key atomically. 24-hour TTL handles edge cases where the same event legitimately needs to resend after a day, like a daily digest. SQS FIFO queues also have a built-in message deduplication ID. Within a 5-minute window, duplicate message IDs are automatically dropped. Good for transactional notifications where you also need ordering. Slightly higher cost, lower throughput ceiling.
Two types of rate limiting, provider level and user level, both equally important. Provider level rate limiting. Every provider has limits. SendGrid free tier, 100 emails per second. Cross that, 429s, back off, potentially account suspension. Token bucket algorithm. Bucket refills at the provider's rate limit, say 100 tokens per second for email. Each notification dispatch consumes 1 token. Bucket empty, message waits in the queue. Queue is your natural buffer. This is why the queue is important even beyond decoupling. It absorbs traffic spikes and delivers at the rate providers can actually handle. User level rate limiting. Sliding window counter in Redis. Key, rate limit user ID push 1 hour. Incur on each notification. TTL resets the window. Max 3 push per user per hour. Max 1 OTP per user per 60 seconds, fraud prevention. Users can't request unlimited OTPs to brute force. Priority queues. Not all notifications are equal. An OTP waiting behind 10,000 marketing emails is a UX disaster. Separate queues per priority. Transactional, high priority, dedicated consumers, reserved Lambda concurrency if on AWS. Social notifications, medium. Marketing, low, runs on spare capacity. यूजर को OTP 30 seconds में मिलना चाहिए. सेल ऑफर 5 minutes में भी ठीक है.
We send the notification. But did it actually arrive? This chapter closes the feedback loop. Every notification goes through a state machine. Queued, we have the event. Sent, we called the provider successfully. Delivered, provider confirms device received it. Opened, user tapped it. Each state transition is recorded in the notification log table. FCM, APNs, SendGrid, they all support webhook callbacks. When a push notification gets delivered, FCM sends a post to your callback URL. Your status handler receives it, looks up the notification ID, updates the status. SendGrid has open tracking, a tiny invisible pixel embedded in the email. When the user opens it, pixel loads, SendGrid fires a webhook. You now know the email was opened. In-app real-time bell. 3 options. Long polling, browser keeps asking the server, any new notifications, every few seconds. Simple but wasteful. High latency. WebSockets, true bidirectional real-time, but stateful. Expensive to scale horizontally, every server needs to know which connections exist. Server sent events, server pushes to client one way. Stateless-ish. Much simpler than WebSockets for notifications, which are inherently server to client. SSE plus Redis pops up is the sweet spot. Each notification service instance subscribes to a Redis channel per user. When a notification lands for that user, Redis PubSub delivers it to whichever instance holds that user's SSE connection. Horizontal scaling solved.
500. You can't fix what you can't see. 3 things you need: metrics, tracing, alerting. Key metrics: delivery rate per channel, P99 latency per channel, DLQ depth, retry rate, provider error rate. DLQ depth is your canary. जब DLQ depth spike करे, कुछ टूट रहा है. Before users complain, you know. Retry rate over 5% for any channel, investigate immediately. Either a provider is flaky or a bug is causing systematic failures. Distributed tracing, open telemetry across every service. Trace ID flows from the original API call, through the event bus, through the worker, through the provider call. One notification traced end to end. Root cause analysis time goes from hours to minutes.
अब पूरा सिस्टम एक साथ देखते हैं. Client hits the API gateway.
Request validated, notification service publishes to SNS. SNS fans out to 4 SQS queues: push, email, SMS, in-app. Each worker picks up its messages independently. Worker checks user preference service, passes the 4 filters: channel enabled, type allowed, quiet hours, frequency cap. If any check fails, message dropped or delayed. Template service renders the content. Rate limiter checks provider quota. Idempotency year checks Redis. Seen before? Skip. New, mark it and proceed. Provider adapter calls FCM SendGrid or Twilio. Response comes back success or failure. Failure, retry with backoff. 5 retries exhausted, DLQ. Provider sends delivery webhook back. Status handler updates notification log. SSE pushes the in-app badge update to the user in real time. The trade-offs we made were SNS plus SQS over Kafka. Traded ordering guarantees for managed infrastructure. Acceptable for most notification use cases. Redis for DDoP and rate limiting. Traded strong consistency for speed. A duplicate notification occasionally getting through on a Redis outage is acceptable. Losing 30% of notifications to a slow DB is not. SSE over WebSockets. Traded bidirectionality for operational simplicity. Notifications are inherently server to client. This system handles 500 million notifications a day. It survives provider outages. It respects user preferences. It never sends duplicates. It tells you exactly when something breaks. अगर आपको रील्स पे ये कॉन्सेप्ट्स कवर करते हुए देखना है, फैन आउट, आइडेम्पोटेंसी, क्यू इंटरनल्स, सब लिंक्स डिस्क्रिप्शन में है. फॉलो करो स्केल टेल पे फॉर द नेक्स्ट सिस्टम डिजाइन.